So today we are going to dissect the fundamental mechanics of blast furnace instability, a subject that determines the line between a high performance asset and a multi-million dollar liability. By the end of this session, you will be able to first quantify the thermal penalty of moisture and fines loading. Second, diagnose the body and descent irregularities like hanging and channeling before they collapse the process. And third is to execute precision recovery protocol for scaffolds and chilled hearth. On the left, the ideal state shows fresh feed with a stable thermal variance of plus minus 1 degree centigrade. But look at the variance state on the right. Notice the moisture accumulation exceeding 5% and the blue shaded fines pocket. This is not just a material issue, it's a thermal disaster. So when you switch to wet stockyard lamp, you are essentially injecting a thermal heatsink into your top. This instability begins with material quality but is physically realized through the mechanics of how these particles settle in the stack of the blast furnace. As engineers, we know that permeability is our lifeblood. Follow panel A and B on this slide. In a belt-top charging system, we see a heavy concentration of fines particle at the stock line periphery, whereas panel B, the bell-less charging, allows for more nuanced distribution. The critical threshold here is 5 mm. Anything smaller than 5 mm is a fine that choke the ore layer pathway required for hot reducing gases. Look at the magnified center graphic. These fines create massive gas flow resistance. And as a operator, we all know it's pretty clear when gases cannot reduce this ore in the stack, that oxygen must be removed via direct reduction in the lower furnace, consuming unbudgeted coke and driving your fuel rate. Furthermore, unmelted fines traveling the wall path appears as a scab at your tweer pip sides, signaling a loss of control. While fines physically block the gas, the moisture riding on those fines create a secondary invisible thermal barrier. Let's look at the numbers. A standard moisture load, just 1% in ore and 5% in coke, inject roughly 33 kg of water per ton of hot metal. This graph plots height and temperature against time. Notice the 100-degree isotherms indicated by the dash blue line. In a wet furnace, this isotherm is forced dangerously low. For material 0.3 meter from the wall, the solid orange line drying time can skyrocket to 40 minutes. Why does this matter? Because reduction cannot begin until the water is eliminated. This delay causes gas reduction efficiency to plummet. Oxygen remains bound to the iron longer and the thermal reserve in your lower furnace is drained to compensate for the lack of stack preparation. We are effectively moving the work of the stack into hearth, which is a recipe for a cold furnace. Detecting these moisture swings is one thing, but reacting to them without a plan often leads to a dangerous and very impactful operation trap. This slide illustrates what I call the wet to dry pellet trap. Follow the circular logic from the step 1 to step 3. Most operators rely on moisture gauges for a baseline correction to maintain a constant dry weight. This is necessary but insufficient because it ignores lost thermodynamic efficiency. So look at step 2. As top temperature drop, the instinctive reaction is to add the fuel. But look at the step 3, the trap. Because dry pellet contain more iron per ton than wet one, a sudden influx of dry feed after a wet spill rapidly cools the furnace due to the increased metallic load. So if you are not charging extra coke 6 to 8 hours before the dry iron arrive at the cohesive zone, you will trigger a thermal cycle that destroy your fuel economy. You must chart the transition, not just the state. So if this moisture is not managed, it doesn't just pass through, it begins to recirculate in a destructive cycle. When we exceed our top gas elimination capacity, we trigger the condensation, evaporation, recirculation cycle. Narrating from left to right, phase 1 shows the normal 100 degrees centigrade isotherm. In phase 2, look at the wall region. Gas temperatures fall below 80 degrees centigrade, causing water to condense on the cold burden. Now look at phase 3. That water doesn't evaporate in the hotter zone below and recondense at the top. This creates a vapor loop indicating by a circular arrows which continuously rub the periphery of metallurgically active heat. To break this, you cannot just wait. You must increase the specific gas volume, often by boosting coal injection to literally blow the vapor out of the top and restore the thermal profile. If you don't, the periphery will eventually go stone cold. To see this happening in a real time, we have to look deeper than just top gas averages. In burden probe, average to top gas is a lagging and insensitive metric. To get ahead of the thermal collapse, we look at the short-in burden probes. These are positioned 60 centimeter inside the hot face, roughly 3 meter below the stock line. Now look at the trend graph on the right. Notice the critical 300 survival threshold. When that probe temperature dips towards 300 degrees centigrade as seen around 8/16, it is an early warning of the moisture driven thermal collapse at the wall. In this specific case, the operator reduced oxygen enrichment by 2%, sacrificing 7% of the production to restore thermal stability. So it's a high price to pay, but it prevents a total furnace freeze. By monitoring the 3-meter sub-stock line temperature, we move from reactive to proactive engineering. So when thermal stability fails at the wall, the physical descent of the burden is the next thing to break. Now coming to the important aspects of erratic burden descent of hanging and sleeping, now enters the realm of physical irregularities. Now look at step 1, breeze formation. This occurs when poorly reduced material, often due to the moisture issues we just discussed, reach the cohesive zone and form a structural arc. Follow white arrow. Follow the white arrow to step 2. Now void is creation. The process continues underneath the breeze, creating a massive empty space in the active coke zone. And finally look at step 3, the slip. When that bridge inevitably collapses, the highly engineered layered structure of your furnace is destroyed. And what is the result? Factor here is operational downtime, recovery from a massive sleep mandate, operating on reduced blast volume for 5 to 10 hours just to rebuild the furnace architecture and those strata of ore and coke again. So it's a massive hit to your monthly KPIs or targets. So while a sleep is a vertical failure, channeling is a lateral failure of gas distribution. Now coming to the preferential gas flow and the cost of channeling. So in the next slide, we are just going to share this. So channeling is essentially the gas choosing the path of least resistance. So look at the gauge on the left. We see eta Cu, the carbon monoxide utilization plummeting from a healthy 49 to a disastrous 36. Very pathetic. The thermal top camera heat map shows a localized brilliant white hot spot on the periphery. These indicate a channel when gas velocities are high enough to blow away descending material. The channel becomes self-sustaining through the fluidization. The chemical energy is quite literally being routed out of the furnace unused. If basic checking, pausing at the end of a cast to collapse the gap, fails to stop this, you must immediately reduce blast volume. And that is the only way out. So breaking the fluidization loop is the only way to force the gas back into the center of the furnace or center of the burden. So these physical disruptions are often magnified by the chemical recirculation of harmful elements like alkali and zinc, which were discussed in much earlier presentation. So the destructive recirculation, we are going to see how the loop of alkali and zinc affect this. So this is the chemical silent killer. Alkali like potassium and zinc enter via raw material but accumulate at level 3 to 10 times their input rate. Follow the white circular arrows at 1350 degrees centigrade. Alkali reduce the vapor at 1400 degrees centigrade. So they bind the nitrogen and carbon to form cyanides, and at 1100 degrees centigrade they precipitate onto solid coke. This is a chemically catastrophic because it acts as a direct catalyst for solution loss, shifting the Woodward reaction equilibrium and degrading our coke strength. So these demands high fuel rates and ruin the permeability we have worked so hard to maintain. So high PCI furnaces require a strong central gas flow specifically to vent these volatile vapors out of the loop before they can recondense, and this is one of the most fundamental for all operators to follow religiously. When these recirculating chemical finally stick to the wall, they form a permanent obstruction as we know. Coming to the diagnostic matrix, uh, and wall that is wall adherence and remediation. So we must differentiate between the scaffold and the scab. This is a very important fundamental that is to be differentiated. So look at the comparison table. A scaffold seen in the internal photo on the left occur in the upper stack and bound by alkali, zinc and fines. So what is the remedy? The cleaning action, lowering the burden to 9 meter and using water spray to cave the scaffold inward. Now look at the scab on the right. These occurs in the wash and are made of resolidified slag. The remedy here is the thermal wash, decreasing slag basicity by a huge margin and charging massive coke blank up to something 15 to 20% of the working volume to melt the blockage away. So looking at the using the wrong protocol, we can say, like trying to wash an alkali scaffold will only waste fuel without fixing the root cause. And this is not only the damage is on the cooling segments, the systems, the asset. So if these adherents are not clear, they will eventually fall and destroy your most critical hardware. Those are the 2 years. And we know the next slide, which is going to discuss about the tear failure taxonomy at the thermal boundary. So tear failures are the ultimate process poisons. Type A shows bottom wear from the high alumina slag, but look closely at the type B. There's the bullet holes. This is caused by a molten hot metal tripping directly onto the copper, boiling the cooling water instantly. Frequent bullet holes are a diagnostic signal. They indicate a dangerously low cohesive zone route. So you need more wall coke to physically lift that melting zone. Type C shows a tip tear caused by a massive falling scab. Any breach of a cooling circuit mandate on immediate unplanned furnace stop. So what is the result of all this? Because water leaking into hearth severely attack your carbon-based refractories and consume local heat, leading to a potential chilled hearth. So every unplanned stop for a 2-year change inflicts a massive thermodynamic shock on the furnace badly. Coming to our important aspects on the thermodynamic shock of stop and start. So look at the operating versus stop graphics. This is a very important graph. When the blast is on, we are at 1400 degrees centigrade. Within minutes of stopping, that temperature plunges to 1000 degrees centigrade. So the melting zone resolidify into physical frozen barrier within no time. So upon restart, the burden cannot descend until this old cohesive zone is fully remelted. And this is why the operational rulebook is so critical. Extra coke must be charged 6 to 8 hours prior to planned stop. So operating at low wind volume during a start without these compensation trigger massive spikes in the hot metal silicon and fundamentally alerts or alter the slag basicity also. So you are essentially trying to restart a frozen engine without oil. The friction is purely thermal. So for longer stops, we move beyond simple compensation into the complex world of blow down and blow in. Coming to our execution parameters for blow down and blow in. As the slide shows, it demonstrates the blowdown curve at the top in our roadmap for emptying the furnace. Notice the intersection of the CO and CO2. The critical abort threshold is when CO2 falls below 10%, signaling that iron oxide reaction has largely ceased finish and raceway collapse is imminent. So now look at the blow in timeline below. It's a 4 node process. Node 3 is the most dangerous. You must wait for burden descent. Crucially, PCI must wait until physical descent is confirmed. Injecting coal into a stationary frozen bed will force fuel backward into the blowpipe, causing a catastrophic failure. So the hearth must be heated to 1500 degrees centigrade and using massive coke blank 50 to 65% of the working volume before you can even think about normal production. So if this procedure fails or if moisture and scab occur, the heat balance is getting affected and you face a cast house emergency also in those conditions. Now coming to the cast house emergencies in recovering the chilled hearth. A chilled hearth is the nightmare scenario and liquid freeze and the connection between the two ear, our heat motor and the tap hole is severed. So look at the recovery vector shown as the bright orange diagonal line. We must use oxyfuel launches to bore a physical channel from the two ear to tap hole. Recovery demands the leanest possible slag basicity between 0.8 and 0.85 to literally cut through the solidified mass. So you must reestablish a cluster of at least 3 adjacent tuyeres to prevent lateral heat loss. If you try to recover with a cold basic slag, you will simply plug the tap hole and stay frozen. So this is about precision chemistry and true thermal force. So to prevent getting to this point, we need the transparent furnace approach. The, what is that transparent furnace approach with the advanced diagnostic control? So, in summary, modern iron making is a transition from lagging thermal indicators to real time spatial mapping. On the left, Soma acoustic pyrometry provides the real time thermal map. In center, 3D radar profile meter calculate exact coke to ferrous ratio. So at the top, IR camera detect fluidization before a channel fully formed. By networking these tools, we can identify and neutralize variance before it becomes a disaster. Stability is not an accident, it is a result of rigorous moisture management, permeability control, and disciplined thermal compensation.